Okay, we're going to talk about sketching vector fields. Now, a vector field, it's the natural generalization of a function to 2 dimensions, 3 dimensions and higher. I mean, you can write f of x in 1D. There's pretty much only one way to write a function, but in 2D, you can write f of xy. This is called a scalar. And because we're in 2D, we have 2 different ways to write something. And so another way is to write, for example, we could have f of xy in our first component, and then g of xy in our second component, and then this is called a vector field. So you know what a vector is, but why field? That just means it's a function of x and y. So vector field, you can think of that as just vector function. Okay, so that means that if you plot a vector field, what it looks like is that if you fix any point, there will be an associated vector with that. So you draw a vector here at that point. So the tail, it's going to be at xy, and then the tip it'll be the vector from that point. So and then at any other point there will be a different arrow associated with because it's a function. Okay, so these things are super useful. So let's just talk about how to be able to sketch them out. So if you have a weird vector field, you can visualize it. So the first example I'll discuss is just a constant vector field. So let's take, for example, I plus j. So what you could try doing if you have 2 components is to write the horizontal and vertical parts. So for example, the horizontal, that's just an arrow to the right because it's I. And the vertical, that's just j, right? So then to get that vector, then we just do tail to tip, as so. And this is I plus j. So to draw this as a vector field, it's constant. There's no x or y dependence. So it's just this vector everywhere. Okay, so I could draw one here. I could draw one here. I could draw one here. I could also draw one over here. And I'm drawing them all with the same length, and I'm drawing them all with the same direction. You don't have to go too crazy. I think this is enough to draw. Okay, so the next example will be less trivial. I think you'll be much more likely to see this one in real life. So what this one is, it actually corresponds to the gradient of the angle function, but in this video we're just going to talk about how to sketch it. So I'm going to break it up into cases. So do x equals 0 first. So when we plug in x equals 0, we get f. We should put arrows above it to be perfectly rigorous with our notation, but forgive me if I'm not perfect with that. If we do x equals 0, then we have yi divided by the square root of y squared. So that's just the absolute value of y, right? So really it's just the sine of y times I. Okay, so for example, if y is greater than 0, then it points to the right. Okay? Now, if I do y equals 0, f in this case will be minus xj divided by the square root of x squared, so that's just absolute value of x, on the denominator, so it's minus the sine of x times j. So for example, if we do x greater than 0, then this is minus j, so it points downwards. Okay? So with this information for these two cases, I think it's worth just plotting these out. So for let's do x equals 0 first. That's the y-axis. So if y is greater than 0, then it points to the right. And if y is less than 0, it switches sign. Okay? Now, if y equals 0 and x is positive, we know it points down. And if we go for x less than 0, then we switch the direction to up. And notice how it's all constant lengths. So that's why I was drawing the arrows roughly the same size. So if we want to do everything in between, you could try one. You could at this point, I would be comfortable extrapolating something like this, because I've seen this vector field a bunch of times. But if you want to get a feel for what's going on, you could try more cases. So y equals x. That's a natural case here. So in this case, f, I'm just going to replace y with x now. So xi minus xj divided by the square root of x squared plus y squared, x squared plus x squared. So that is just x times I minus j times square root of 2 times the absolute value of x. So we get the sine of x, then I minus j. So again, you do the horizontal and vertical. So horizontal is plus I, and vertical is minus j. So now I'm going to connect these downward, and that is I minus j. So this will then be for x greater than 0. So for x greater than 0 and y equals x, let me just quickly draw y equals x here. It's going to be pointing southeast. And it'll be northwest on the opposite side of x. Okay, now you can get a feel about what's going on, and I can start filling in the rest of those vectors. Okay, and if you like to draw a streamline or a flow line of the velocity, this would be how the particle. This is the particle trajectory. If f is the velocity, then that's that flow line. That would be the trajectory it follows. It would just be moving in a circle. Okay, so I think we can talk about another example. The example I'll talk about is a very simple one at first glance. So f equals x times k, where k again is the z unit vector. So let me just do f equals k for a sec. It's literally just k everywhere, right? So you're just going to draw arrows wherever you see a point, and every point will have that same constant vector field. Now, how does it change? How does x change it? So if x is greater than 0, then it means it's pointing up. And if x is less than 0, it will point down, right? Because an example, if x equals 1, then you just get k. If x equals -1, you get minus k. Okay? So another way it changes is that for small x, small arrows. So for example, x equals 1 over 100. The vector field is actually k divided by 100, so it's very, very small. So what I'll now do is I'll try to draw the vector field, and we're going to change it according to these two ideas. So let me just draw the negative x-axis right there. And what I will do is I'm going to draw very small up arrows near the origin, very small down arrows, and then I'll draw a few big arrows as we get farther away from x equals 0. So then after you do this, the y and z, if you shift y and z, it'll just be the same, right? So in this way, you can get a kind of feel for what's going on. The vector field collapses near the yz plane. And it grows away from it. Okay? So kind of in that narrow region, you have a very small, stagnant vector field. Okay, let me just talk about one more example. And it will be f equals xi plus yj plus k. So notice now this is just, this is basically just r, right? But now but it's kind of like the 2D version. And so now it's just a constant z part. So if you were doing 2D, I would draw r as you take any point and draw an arrow in the same direction. And you could do the same length as well. So for example, this is our point xy. You could draw an arrow of the same direction and length. If this was our x and y, I could draw an arrow with the same direction and length. Because that is what the vector field r actually represents. Okay? Now, if I'm doing 3D, I want to add k to this vector field. So let's again try to sketch out a few arrows. So if I'll do dotted lines for the 2D stuff. So if we choose this point, then that would be the 2D version. But now I want something 3D, so I'm going to shift it up. And if I were doing the 2D version on the y-axis, you might have this vector, but now I'm going to shift it up. Similarly, if I were doing a vector here, then I might shift this up. And just to indicate, I might also indicate there are some angles here just to try to tell yourself that there are pointings up. Okay? So you don't have to get too crazy with it. But this kind of gives you a feel for what's going on. Okay. Thanks for watching.